all the 1 times, all the 1 times. Do it for the USA.
Good morning, everyone. Unfortunately, I couldn't get the real Barack Obama to do a dance track for FOA, so that is as close as we are going to get for the semester. Perhaps someday, if some of you graduate and go on to be President of the United States, you'll do us a favor and come back and make one of those music videos for us. Starting off every week as we do with one of our figures, this is Commodore Grace Hopper, U.S. Navy Rear Admiral, who was born in 1906 and 1992. And in her honor is named the Major International Conference for Women in Computer Science and in Computing. So hopefully a number of you will get a chance to go and participate. It's a wonderful opportunity. One of the things that Grace Hopper is famous for is for developing the concept of machine-independent programming languages. In the early history of computing, each computer and each architecture would actually have its own programming language. You had to understand the design of the computer itself in order to program it. So if a given computer would have a certain bank of switches and dials, you had to learn the right combination of switches and dials to program that particular machine. And even once we moved past manual computers and we moved into programmable computers, at the same time, you needed to know the details of the low-level assembly instructions that that particular computer would operate under. Grace Hopper came up with the idea of having a higher-level language that would then be independent of the particular architecture, which you could use a compiler to convert into something that your particular computer would understand. She is also one of the primary inventors of the compiler and did a lot of the heavy intellectual work that was necessary to conceive of them. She was also adamant that computers could be programmed in English, and perhaps in the last year we've seen the beginnings of the fruition of that vision with ChatGPT and some of the like. So we're going to keep her in mind as we go through our content this week. And we're going to start off by asking a bit of a different question. So we already know how to sort things. We have a bunch of rudimentary data structures. But again, we haven't considered the limits of our particular machines, or even more, the limits of the data that we might attempt to operate under. So our motivating question for the start of the week is, how do we sort a humongous amount of data? So not just when I have a small array with 100 items. How do I sort an array that has 100,000 items or 100 million items? Now, I'm going to take one or two answers from the room. How do you think we could go ahead and sort an array of 100 million items? Who wants to get us started? Max.
We could either wait a really long time or get a better computer.
Okay, we can get a better computer. Other ideas? Pass the microphone down.
We can find a better sorting algorithm.
What do you mean by better sorting algorithm?
That's better worst case complexity.
Better worst case complexity?
Trying to find a time sorting algorithm.
Oh, I don't think one of those exists, but we could try. Any other ideas?
This might be a dumb idea, but if you have a really large amount of data, you have a certain sorting algorithm that can be parallelized.
Oh, that sounds like a good idea. What do you mean by parallelized?
Well, what you could have is, if you have a certain sorting algorithm where basically certain subsections of your array can be sorted, I guess independently, you could have multiple computers performing the algorithm. You divide the work required over a large amount of computers.
Yeah, so instead of having a better algorithm per se, we could have an algorithm that allows us to split the work up into a bunch of different chunks and then work on each chunk independently. Maybe you have 10 computers, and then we need some way at the end, once each computer is finished with their chunk, what do we need?
We need some way of merging it back.
Merging them. Okay, that sounds like a good word. Let's get back to that in a second. The general name for this strategy is divide and conquer. And as Oliver just said, it was Oliver, right? As Oliver just said, we need to split up the work so that half the items might fit in one chunk and then half the items go in another chunk. And we could even split it into four, give each chunk to one of our 4 computers and then merge them. We need some way to do that. But we're gonna come back to this in a minute. When we take our initial humongous amount of data, we have a bit of a problem. How much memory does your average computer have? Now, I've asked this a couple times in class before. Oliver, you can just give me an answer to that one.
Half the amount of memory a computer has.
Yeah.
Well, I actually forgot. this one, I'll be honest.
Do you know how much memory your computer has?
My memory, I've got 64 gigs of RAM.
64 gig of RAM. Someone plays games?
Yeah.
Yes. That was a good answer. Okay, so 64 gig of RAM, that's quite a lot, can fit a whole bunch of numbers. But what happens if we exceed the 64 gigabytes? What can we do? Dux, do you want to take a stab? So we've used up our 64 gigabytes of RAM, but I have 100 million or 100 billion numbers, whatever it takes. What can we do with it?
Can use the hard drive.
You can use the hard drive. But unfortunately, thus far in the class, we haven't yet figured out how to use the hard drive. What do you typically store on a hard drive? Files. So I have one example file here, but just as like this file is C code, I could have a file with some numbers on it instead. And then what I want to do is I want to break up my large array into a series of files, transmit each file to a different computer. Each computer will then sort its file, send them back, and then I need some way to merge them. And so this is going to be a bit of a tricky, complicated process. And there's also quite a trade-off involved because our hard drive is going to be much, much slower than our RAM, our main computer memory. So what we don't want to be swapping things in and out of a hard drive. It'd be much better if we could load whole chunks into RAM, sort the chunk, put it back on the hard drive, and then at times when we need, we can fetch things back from the hard drive into our RAM to do it quickly. And this takes us to our next sorting algorithm called Mergesort. Now, Mergesort doesn't have to be done in this complicated way with breaking up files, but it is our motivation for talking about it. We want to understand this general process of dividing up a problem, in this case it's going to be sorting, solving it in lots of independent units, and then combining them back together. And this is a pattern that you've probably seen in a few other places in class as well, but Mergesort is a particularly good example. So what I'm going to do is we're going to work through this algorithm organically on my iPad and see if we can come up with it. So here I have some numbers. We're going to sort as we did before, but now we're going to try this process of breaking things up and putting them back together. Emer, do you want to help me out or no? Okay, pass the microphone over and we will work this algorithm out together. So what was the general strategy we just talked about?
To like split up the data set into smaller chunks. So here we have this.
We have 1, 2, 3, 4, 5, 6, 7 numbers.
So you can't have like equal chunks, but I guess if you have like one element this time,
Yeah, so one of the sides could be a bit larger. Let's break it up. So tell me where I should put my red line to break it up.
go 8, 7, 16, and then 31.
Okay, so we've broken it up into 2 chunks. Would it make sense to break it up into more chunks? What do you think?
Maybe not in this case. So we don't have too many data sets here.
So hold the microphone a little closer, otherwise it's going to be hard for everyone to hear. But okay, so one answer could be, we shouldn't break it up more because now we've got small enough chunks that we can sort. And how do we sort things?
We could either like move and then go through, and then move it to where it sits.
We've got a few existing algorithms, right? But let's see if we can develop this algorithm further. So if we're going to take this algorithm to its logical extreme, what's the next step?
To sort them from smallest to largest.
So that would need to have another sorting algorithm. But assume we don't have another sorting algorithm. Can we repeat the process that we just did again?
Yeah.
Okay, so let's do it with our left half first. So what's the next way to break it up?
You want to find which one's the smallest and which the one. So you just start from 16.
Wait, this is too much for our computer's memory. We're going to have to break it into smaller chunks, right? So what are the chunks that I can break it into?
You could do 8, 7, and 16.
So I could do 8, 7, and 16, but going like we did before and keeping the smaller chunk on the left if we're off by 1. Let's do that again. So we could have 8, 7, 16, and then we break that up into 8, and then 7 and 16. And let's keep working on this chunk for the time being. Now I've got 2 chunks there. Is my left chunk sorted?
There's only one.
There's only one, okay, so it's already sorted. What about my right chunk?
Yeah, if
It's sorted as well. How do I know that it's sorted?
there's 7 smaller than 16.
7 smaller than 16, so one way that I could say it's sorted is by, when I have 2 items, I could just do a comparison of the 2 items, Or I could even go one more layer down and break it up again. And I could break up 7 and 16 into 7 and 16. Okay, but now we need to go backwards. So I have these two chunks on the right. I have my 7 chunk and my 16 chunk. And I need to figure out if they're in the right order. So now what am I going to do? Now I have to do my comparison. So at some point we can't get away, we can't get out of doing comparisons and sorting. It's just a fundamental part of it. So my 7 and my 16 are in the right place. And so we can combine them. And so now we have an array with 7 and 16. But I've got another sorted chunk that I need to merge it with. So how am I going to go about doing this?
Just compare the two. Compare 3 elements, I guess, and find a place for each.
But we don't, comparing 3 elements isn't something that our computer knows how to do. We can only compare elements like one element with another element. So how should we start this comparison? It can be a multi-step process.
Could you not just use insertion sort, I guess?
So I could use another sorting algorithm, but let's see if we can be cleverer than that, because we know that both the left half is sorted and the right half is sorted. So maybe I can take advantage of that. So which 2 elements should I compare? Let's start with that. 7 and 8. And which is bigger? 8. 8 is bigger. So we know that the 7 must be the first element in our array, right? It's going to be the first one in our final one, because we only have 2 options, and one of those 2 elements must be the first one. So let's keep a pointer to the start of each of these arrays, and we'll say, you know, the 7 is the one that we're going to put in our final array first out of these 2. Now, we're done looking at the 7 in this one, and so let's move our pointer up. Now it points at the 16. Now what do I do?
You see that 8 is smaller than 16.
8 is smaller than 16, and so what's next?
So 8's going to be next.
8's going to be next. And now I don't even need to bother looking at whatever's in my right chunk. I can just put it in. So now I have another sorted chunk, 7, 8, 16. Okay, let's leave that there for the time being. But I've got another half of my array I have to deal with. So help me through this.
Split it up into 2 chunks.
Split it up into 2 chunks. So I'm going to get, 2 and 9 and 34 and 12. Now what do I do?
You can branch them up again.
So 2. Okay, now what?
Now you have just 4 numbers that you can.
Okay, they're all sorted. So we have to do, what was the other step called? When I put the 2 things together, what word was I using? Do you remember? Merge. Okay, so this is our merge step. Okay, so which 2 things am I going to merge first? 2 and 9, and how do I merge them?
You compare 2 to 7.
Well, I'm not looking at the whole left half yet. I'm only looking at my 2 and my 9. They're this branch. And what do I do? 2 smaller than 9, so I put 2 first and then 9. So 2 and 9 were merged back over here, and on the other branch?
You find that 12 smaller than 34, so you do 12 there.
12 and 34. Okay, so now I've got my 2 arrays over here, and I have to do my, what step again?
You compare
What was the step called?
merge.
Yeah, the merge step. Okay, so let's put our pointers in there, and I'll rub out the other pointers so they don't confuse us. Okay, so give me instructions.
Well, you can either compare 2 and 12. You can see that 2 is smaller than 12.
So 2 is smaller than 12, so which of the elements will be first? 2. Okay, now can I put the 12 in?
We need to compare the 12 to the 9.
Yeah, so I have to move my pointer up to the next element in the subarray.
And you see that 9 is smaller than 12, so 9 goes next.
9 goes next. And now what happens? It's done, so we just put the remainder elements in one by one from the other side. Okay. What step do I do?
Same step again, just with these 2.
The merge step, right? Gotta say that word so it sticks in your brain. And what do I need to do the merge step? You can direct now.
You can compare the the pointers on 7 and 2. 2 is smaller than 7, so 2 goes first.
2 goes first. Now what happens?
And then we move the pointer on 7 to the pointer on 8.
Yeah, we've got the hang of it now. We move the point. Oh, did I hear you say the right thing?
What would be the benefit of moving that one along instead of the other one? I guess because you know.
So we know that this element is no longer eligible to be placed anywhere anymore because we've already placed it in the final one.
And then you compare 9 and 7. 7 is smaller, so 7 goes. And you move 7 to 8.
Okay, let's move our pointer along. I'm not sure if this will. No, I'll have to do it manually.
Compare 8 and 9. 8 is smaller, so 8 goes in. And then you remove the point from 8 and move it to 16. 16 is bigger, so 9 goes in. And you move the pointer from 9 to 12.
Give me a second. Move the pointer from 9 to 12.
Then you compare 12 and 16. 12 is smaller, so you put it in and move the pointer from 12 to 34. 16 is smaller, so you put it in, and then you can just put 34 at the end.
And we're done. And if we zoom out at the top, we now have a fully sorted array. So it turns out we didn't need another sorting algorithm at all. We could repeat this process of dividing and conquering over and over, where we divide it, up until we get to a base case, which is trivially true. And then we just need to find a way to combine our base cases using a what step? A merge step. Thank you very much. Can we have a round of applause? And we can give you a t-shirt for that one. So it's time to write out some code for it. Fortunately, this time I'm not going to make you do it on your own, but the code for merge sort is also pretty simple. Just like heap sort that we saw, merge sort does not take that many lines. So the very first thing we do is check if we have one element alone in our array that we're trying to sort. If we have one element, what do? We return. It's already sorted. Then we do our split into 2 chunks. Then we do merge sort on each of the chunks. And after we have done merge sort on the 2 chunks, then we call merge to combine the 2 chunks together again. So the basic idea is, if you know, just like with our recursive examples earlier in semester, if you know how to solve a smaller version of the problem, then you know how to solve a bigger version of the problem. Because you can take your smaller version and do the step that you need to take to combine the smaller versions and make the bigger versions. So it turns out that recursion can also be thought of as divide and conquer in many cases. The only tricky bit is our merge function, which actually requires us to keep track of these pointers. Now, in the version that I did on the iPad, as well as the one up here in the pseudocode, we are using an auxiliary array, where I have a second array that's going to take the elements from the sorted smaller chunks and put them in some larger, bigger chunk. Now, you don't actually have to do this. There's a version of merge sort that is in place. That means we don't need an auxiliary data structure. We don't need another final array where we're going to put the things in. But getting there is a challenge for you to work out if you're feeling comfortable with the course material. Try and see if you can work out your own version of an in-place merge sort. So how does our merge sort actually work in the code? We have our auxiliary array, which we are going to start filling with, that's our array T, that we are going to fill with all the items on the left half. And then we're going to have our 2 pointers, which will be at the relevant parts of the array. When I say relevant, I mean starting at the left side of the smaller chunk and the left side of the bigger chunk. While your left pointer has not exceeded the bounds of the left chunk, and while the right pointer has not exceeded the bounds of the right chunk, compare the elements, the element that you're up to on the left chunk, the element that you're up to on the right chunk, find the bigger one, put it in your final array, and then move up the pointers as we did before. And that's pretty much the entire algorithm. So we're going to sort an array of 100,000 elements. We're going to use our sort scaffold as well to just get a feel for how long it takes. And unfortunately, this implementation is not going to work for like the 100 billion size array that we've done so far. For that, we're going to need files that we will see right after this. So this will need sort scaffold. Then we have 3 functions here. We've got recursive merge sort as well as merge sort. The reason why we have these 2 is we want to have a helper function within merge sort that is then going to make the call to the recursive merge sort that helps just set things up. It's not actually necessary, it's not part of the algorithm, it's more part of the C structure that we use to help us run the algorithm. So our merge is pretty much identical as we saw before. We just have this copy data function to abstract out some of the details of how to put things into the array at a given point. Then our recursive merge sort is very few lines. If you only have one element, return, otherwise calculate the mid, do merge sort on the left, do merge sort on the right, and then do a merge on the overall algorithm. And then our merge sort helper function here is just going to make the call to merge sort and malloc enough memory for the auxiliary array. So I remember how we said how we're going to keep this extra array around that we were going to copy the final elements into. That's our array T over here. And we just need to make sure to create it independently, and this is why we're actually using the helper function. So let's give it a run. And we have our merge sort. Now, it turns out that in practice, we're still generally going to use quicksort for things, even though we have heap sort that has faster worst case time, and even though we have merge sort that allows us to potentially sort really big things. Now, remind me again why we might still use quicksort a lot of the time. Yeah, Oscar.
When we talk about time complexity, we're not really considering the actual execution time of the function. Perhaps merge sort or heap sort is a lot more open than sort, because the constants in the time complexity which we don't consider might be larger or less.
Yeah, so Oscar says that the big O time gives us a sense of bounds, on worst case bounds, and they only tell us about proportionality. They don't tell us about the actual constants or the actual running time of any of these algorithms. And quicksort for many types of real world data will end up being the fastest. When we get to very large data or special purpose data, we'll start then maybe considering merge sort or another special sorting algorithm. So we've done our like hand-washy version of running merge sort. We see that it runs very well, but we also need to actually do what we've done with all our algorithms and calculate this worst case bound, even though we already know that we're going to use quicksort mostly for small arrays and merge sort for super, super big ones. It's still worth having a handle on how that behavior scales. Why? Well, even when we move to really big ones, we're going to want to know proportionately, if I say double the amount of data, how long is my big merge sort going to take? So we have to do the analysis. To do our analysis, let's see if we can get our recursion relation before I display it on screen. How many chunks at each level do we split our data into? Yes. Yeah, 2. Sorry, I was saying yes to Nadine because I saw her holding up the number. So we split it into 2 chunks. And then in each chunk, how much work do we have to do? Assuming that the chunk now has n items.
1.
So what's the 1?
So as in if the n is more than what you divided, otherwise.
Yeah, and then when we're finished doing the dividing and the calls to the divided bit have come back, how many elements do we have?
1 on each, right?
Well, if we're on the second level from the top, we'll have, let's say, let me start this one again. Instead of it, let us separate out 2 variables. So n will be the number of items in the total array. At each level, though, we're going to have L elements. So we'll start with n. The second element will have n on 2. And let's call that L for the time being. And then the third level, we'll also still use the same variable L, but L will refer to how many at that level. So let's say we're on the second level from the top, right? We have L on 2 elements in the left chunk and L on 2 elements in the right chunk. How many comparisons do I need to do? So let's go back to I'll give you 1 second. Let's go back to our schematic of merge sort. Let's go back. There's our schematic of merge sort. So I've done a recursive call on the left, a recursive call on the right, and how much work do I have to do in addition to those recursive calls?
I mean, it really depends because in her case, one of the arrays just matched because the last array was the first array.
but can we bound it? Let's say there are L items total in this level, L on 2 and L on 2.
So it will just be 2n.
Why 2L?
The 2n.
Well, there are only L elements, so we need to do
Okay, L.
just L comparisons. So we get L plus 2 times, because we've made 2 subchunks, and each of those 2 subchunks are going to take the time for merge sort on half that chunk. So well, let's put these pieces together and make it a little clearer. Our time is going to be bounded by the following expression. For each level, we have to do our 2 recursive calls on half of the items in the level. And we also have to do n work, because at the end, we're going to have to do that merge, which requires us to look at each of the items in our sub-arrays that are now sorted. So we get this expression. We get n plus 2 t of n on 2, where t is the runtime of merge sort. Now, obviously, this refers to itself. It's a recurrence relation of what we've seen before. So we have to further break it down. But as Afan said, if we only have one item, we don't need to do the merge process. All we do is one step, and that's return. So we can use this to go from our base case back up to the overall analysis. So here we get a little bit mathy, but you've seen this process before. In fact, we've seen a very similar recurrence relation before. So up in the corner, we have our n on 2k equals 1, n equals 2k, log n equals k. So this is just asking how many times can we divide our n items? To what power of 2 does it need to be divided before we get left at one item? So if you halve it, and then you halve it again, and then you halve it again, and you halve it again, you can do that log n times, where n is the total number of items. So we know that there are going to be k terms in this expression over here, where we've done n work on 1 on 2 to the 0 plus n work by 1 on 2 to the 1 plus 1 work on 2 on 4, et cetera, et cetera. We know there are k terms in that. And if we substitute that out, we can then bound it by log n. So we get a total runtime of t of n is less than n plus n on 2 log n, which is big O of, says at the bottom, someone tell me, n log n, yeah. So we have n out the front, we have log n terms in the middle, and they're all constants. So we get log n log n. And that is our worst case runtime. So here is the challenge, which is to write merge without an extra array, so doing it without the auxiliary array. In some words from Alistair Moffat, this is a good way of helping you to remember between quicksort and merge sort and their behaviors. Quicksort is hard split because we had to do this complicated pivot thing, and then we had to move all the items into the right side of the pivot. But then it was very easy to join them. We just attached the 2 sides. Merge sort was easy split, but hard join, because when we do a join, we then have to follow the whole merge process. But now that we've done this, we want to do it on our super big array, which requires us to learn a little bit about files. Now, the rest of the lecture is going to be dedicated to learning how to do this in C. Obviously, this isn't necessarily an algorithmic thing, because every operating system is going to have a different way of working with files. But for our purposes, because we're working with C, and we're using Windows subsystem on Linux, or Mac, which is very close to Linux in some ways, the following things are all going to apply to those systems. If you want to do Windows, go take another class. So these are the main functions that we will need to at least get started. Open file, close a file, read a file, and write a file. In Unix, it's actually quite interesting in that pretty much everything in the operating system is a file. So you want to read from a CD, it's treated like a file. You want to figure out what processes the computer is running, there is a file with a list of all the processes. You want to read from an arbitrary part of the computer's memory, there is a file that you can read from called mem that contains access to the entire computer's memory. And so this is kind of cool. So with these few primitives, you can actually control pretty much all the runnings of a modern Linux operating system. However, not every file is written in a way that humans understand in plain ASCII text. Some are binary files. What this means is the program that has written the file has decided to encode its data in some way that is more efficient. So what kind of encodings have we seen thus far? Afan, you have the microphone? You want to pass it on? Either way. What kind of binary encodings have we seen so far?
ASCII and hex.
So ASCII was not a binary encoding. ASCII was a ASCII encoding, was the human readable one. What things do we encode not in ASCII? Hold the microphone up a little more. What other types have we used in C?
Oh, insert.
Yeah, so do you remember how an int is represented?
Each is 8 bits.
8 bits, and a bit is it's in binary, yeah. So all of our other types that are not ASCII are binary types. So if you were to look on the hard drive or look inside the computer's memory and try and figure out, okay, how is an int represented? An int is not represented in ASCII. There's a difference between the string 42 and the number 42 represented in the computer's memory. And when we write a file, we can choose to write strings, like write it in ASCII, or we can choose to actually write the binary data. So we'll see how to do both of these in just a minute where we look a little more at syntax. So all of our file functions are going to take an argument that is a file pointer. Now there's nothing particularly special about a file pointer other than that it is a pointer to a file type. So the natural next question is, well, what's a file type? The answer is this thing. Now you don't have to know about this, you don't have to care about this because all the functions hide this for you. The only thing I'll point out actually a couple features here. So the first thing is the file underscore file over here. That's an unsigned char. Now this is just a number. On typical computers, they'll go from 0 to 65,535. And all it is it's a link that the operating system has given your process between the file that you're trying to access and a number that it stores in a table. So when you go to write a file, you'll use this file pointer, and then the operating system will look up in its table, okay, you asked for file number 3, and file number 3 in your program is, let's say, file number 4, let's make it. File number 4 in your program is hello.txt. Now, why might we have the operating system do this? Why wouldn't we just store the location of the file directly? Do you want to pass it on to Haruki? Okay, so how many files are on a typical computer? Just doesn't matter. Give me a lower bound. A billion. And how many files is my typical program going to open? A few. It doesn't really matter how many, but somewhere between 1 and 10,000 seems reasonable. 65,000 seems like a lot of files for one program to have open at once. So if we're going to efficiently navigate between all the files that our program has open, it would make sense to not store a table of all the files and whether they're open or not. It might make sense to just have a mapping for each program which files are open in that particular program. And so that's one of the reasons we use this. As well, putting a cap on how many files a given program has open helps the operating system to make sure that one individual program isn't hogging the entire file system. The other thing that we're going to have is we're going to have a pointer to some part of the computer's memory where the computer has loaded up the file into RAM, and as well to say where that file starts in the computer's memory, as well as which part of that file your computer is up to reading. So you don't always want to read just the first byte over and over and over. You might want to read the second byte or the third byte. Just like we do in scanf, how you want to move along the stream so that you're not just stuck at the start of the stream, we need to have some pointer that the operating system uses to keep track of where in the file we are. Now all of this might seem highly technical, but keeping this in mind will help make it a little easier when you try and understand how to use files. Now, I said file 3 before and then changed my mind and said actually file 4 should be hello.txt. Why? The first 3 numbers are reserved. Sorry, file 3 actually would have been okay. I made a mistake. The first 3 numbers are reserved, but we start at number 0. So the first 3 numbers are 0, 1, and 2. And these refer to our 3 built-in streams. Now a stream is just one particular way of reading a file that treats it like a pipe that you can turn on and let stuff out of or turn off, but you can never go and see what's like higher up the pipe. You've only got 2 things you can do. You can open the pipe and let the next thing come out, or you can close the pipe. So this is the stream version of files, and this is what we do with printf and scanf, is we treat three different things that are actually files as far as Unix is concerned as streams. And these are standard in, standard out, and standard error. So when we do printf, Haruki, which of these do you think we are using?
Printf would be output, so I would assume it's standard out.
Yeah, so we're using standard out, and we're using the stream version of standard out. And when we are reading in with scanf,
It would be standard in,
and when we get a segmentation fault,
standard error.
yeah. So there's this special last stream reserved as well, standard error. Why do we have standard error? If you think about it, when you're running a program, in our class, we've been piping things into our program. And you can also pipe things out of your program with the different angle brackets. Let's see if I have a nice example somewhere here. I've got this nice example here where I'm running my program, I'm feeding things into standard in, and then I'm taking everything that the program outputs from standard out, and I'm putting it in file 2. So in is file 1, out is file 2. But my program might have an error, and if I'm feeding all of the output from my program into file 2, I'm not going to see the error message. The error message is going to go into file 2. But as the user of the machine, I probably still want to be able to see that error message. So instead of putting all the error messages into the same place as the output, the Unix philosophy is to separate that out into another stream that you can then independently control and see on the screen. So even if you've redirected standard out, you can still see if your program has an error. Now there is a way if you want to put the errors into a file as well, you can do that. Or you can put the errors both in standard out and standard error. It's up to the computer is at your command to do any of these things. So this takes us back a minute to our printf and scanf functions. These are just wrappers around more complicated functions, fprintf and fscanf, that actually explicitly have the streams that they're writing to in there. So in this case, fprintf is the same as printf, only it takes standard out as the first argument, and fscanf is standard in. Now the other thing we need to do, we need to tell the operating system how we're going to use the file. Are we going to open it for reading, writing, or do we want to actually add to what's already in the file? Now, I just said something a little funny there. Do we want to write or do we want to add? This is something that is pretty tricky with Unix files that you might screw up a bunch of times. If you open a file for writing, you'll actually clobber everything that's in there already. You'll delete everything as soon as you open the file, as I say on the warning there. So if you want to add something to what's already in the file, you have to open it with the A flag. And these are all going to be flags that we'll use in our functions in just a moment. And you can also add the plus sign if you want to go into the file, navigate to some arbitrary point, and then start reading and writing from that location. Okay, we're ready for a few demos. Let's try some live code. So this is a program I've not yet written, although I have a cheat sheet. We will try and write a piece of code that accesses a file. So the first thing I'm going to do, I will copy my headers from over here. Okay. So now I am going to check my man page very briefly for how fopen works. So fopen, okay. First needs the path to the file and then the mode. So we know both of these in theory, because this will just be my file name, which is going to put a file in the current directory. And then the mode, I had it on my slide just before. So assuming that this file doesn't already exist, what file mode should I probably do? The file doesn't exist. I want it to exist. Yeah, Max says W, so let's put in W. Now, is it a good idea to ever just use a function like that? What don't I know about this function yet? At this point in time, when I've reached line 10, there are two things I don't know. So firstly, what am I doing with the output of this function, right? So let's go into our man page. So it tells me about the mode. And it looks like I might have made another mistake. const char star restrict mode. So is W a char star? Is this a char or a char star? It's a char. And a char star is also known as a string typically, as long as it's null terminated. So this is saying, you know, where we're going to use a string, and we need that because if I want to do the special random access mode, I need 2 characters, and obviously one char doesn't fit 2 chars. Okay, so that's fine, but there's definitely more to using this function. Let's see, let's scroll down. Okay, upon successful completion, return a file pointer, otherwise null is returned and the global variable error number is set. So what am I missing? What was your name again? You got to hold the microphone up. Yulong? Yeah. What am I missing on this line? It says, upon successful completion, returns a file pointer. So what am I missing? So fopen has returned, and now I actually need to capture what it's returned. So let's call this fp. It's going to be our file pointer. And the other thing, it says, upon successful completion, otherwise null is returned. So what do I need to check? It says if it hasn't been successful, it's returned null. So what I'm going to do is I will check that the file pointer isn't null. I always need to do the check because if it is null and then I go on using it, then I have made an incorrect assumption and my program is going to behave in ways that I don't expect, and I might even cause a seg fault because I might try and dereference a null pointer. So now I can use fwrite. Let's go to the man page for this. And you won't be surprised to see that fwrite takes in a pointer, how many items and how large each item is. Okay, so now we actually need some stuff to write to it. So let's try writing an array of characters to it. That'll probably be a nice, simple thing for us to do. So let's look at this carefully. Function fwrite writes n item objects, each size bytes long. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Size of will work in this case. Or I could use stringlang a. But to use stringlang, I will need string.h as well. Now, function fwrite writes n item objects, each size bytes long, to the stream pointed to by stream, obtaining them from the location given by pointer. So let's check fopen again and just see what it gives us back. So it's giving us a file pointer and associates a stream with it. So it seems like we can use our file pointer directly as a stream. So let's go back into fwrite, follow along carefully. I'm showing you this so you can get a sense of how to read the man pages and write a program on the basis of functions that you don't yet know. So writes n items, so how many items are we going to have? Yulong, do you want to pass it down to Junji?
Length item.
We're going to have length items. How large is each item?
Char.
1 char. And how big is a char? It's not a 1 bit, 1 byte, but we could do size of char. The first argument is a pointer to what? Let's see what it says here. Function writes n items objects, obtaining them from the location given by pointer. So what should my first argument be? Is that the location where the items that we're writing are coming from? Or is that where they're going to? Going to. So where are they coming from? Where are our characters coming from?
From A.
Yep. And our last argument writes to the stream pointed to by stream. So what should our last argument be?
FP?
FP. So let's try this, and we're going to run out of time in a second, so we will compile that and run it, and then keep building our program tomorrow. Oh. It's going to ask me to save this somewhere. Just going to save it to my downloads folder to be fast. So let's run files. And now if I look in my downloads folder, I should see, what did I call it? Hello.txt. Let's open it in Visual Studio Code. Let's say open. There we are, hello world. And it looks like I've put the null byte in the wrong place. So for the very last thing, not the null byte, the new line. Let's move the new line to the correct place. Let's run GCC, compile it again, run files. Now what do I expect to see when I open hello.txt? Now I see the correct one. Why did it not just add to the end of the file? What did I do? No, not terminated it. Say it again a bit louder as a group. I overwrote it with the W flag. So if I wanted to append to it, I'd need the A flag. Let's run this. Let's take a look. And now I'm appending to it. And I will see you tomorrow. We'll finish off files, and then we will start moving towards the end of the class. Thanks, everyone.